Well, let me start out with acknowledging ITAMP as a wonderful institution that houses many of these wonderful workshops. That's really great to have. And let me thank in particular the organizers for inviting me. I appreciate that a lot. And this is a nice meeting that brings people from different backgrounds together. Is the camera on? Okay. Okay, now my time starts. Attosecond science, I want to give you a flavor of what we are doing in trying to resolve in time electronic processes, electronic motion. And the big outlook is that you envision being able to see how molecules form chemical bonds, that's electronic glue that is redistributed, or break electronic bonds. And all of this is driven by laser technology that has now made this possible and provides ultra-short light pulses with durations down to 40 attoseconds. The collaborators I already mentioned, Maya, Aihua, and Jason are graduate students, and a lot of the credit for this talk should go to my former postdoc, Changhua Zhang, and my current postdoc, Qing Liao, who have both been working on complex targets. The outline here, I thought I cover two topics, and I felt that's appropriate for this particular workshop. And the first topic is on atoms, so strict photoemission on atoms, where I talk about how to describe, how to characterize photoelectron wave packets in their spectral profile. I'll show you what we mean with photoemission delays. There's still some controversies, there are different definitions, so that is essential. And then discuss how the very process of trying to do this time-dependent measurements using a combination of an XUV pulse, ultra-short, and an infrared streaking pulse that you can view as part of the measuring apparatus, how the infrared pulse, so the process of measurement, influences the initial state, influences the target that you want to get some information about, and influences the final state of the photoelectrons. And along the way, I briefly cover some of the methods that we are using for that S-matrix, strong field approximation, iconal methods, and brute force Schrödinger equation solutions. In the second part, I will then talk about photoemission from complex targets. I had in mind to just talk about solids, but if Maxim is still here, if I have time at the end, I will throw in an extra graph with an idea that we just have on nanoplasmonics in nanoparticles. I hope we get there. So I will then show you examples of photoemission delays from surfaces, from complex targets, and talk a little bit about a possibility that we think is now really opening up for probing time-resolved collective modes in solids, plasmonic modes, polarons as they move. And that also then has to do with the interpretation of time delays that is still going on in the literature and is led in a somewhat controversial way to this day. So let me start real simple. If you have an ultra-short pulse, and keep in mind those pulses can be 100 attoseconds, and ionize an atom described by this Hamiltonian, you generate a wave packet, and this wave packet is part of the time-dependent state of the system, which may have some bound contribution. We're just assuming there are no excited states, and which has a continuum distribution, which for large time describes your photoelectron wave packet as it moves to the detector, and which can be composed of continuum states of this atom as a convenient basis. And so to describe this photoelectron wave packet, what you got to know are the expansion coefficients. Those you can calculate, in the simplest case, by solving Schrödinger's equation to first order in the XUV potential. That's good enough. And so you get this very well-known expression for the expansion coefficients. You know your wave packet. If you then, in addition, take the electric field of the XUV pulse, or associated with it the potential in dipole length form, and spectrally decompose it, then you can put this spectral decomposition of the potential into your expression for the coefficients, and then into your expression for the photoelectron wave packets. And what you get is a photoelectron wave packet now written in terms of the dipole matrix element that gets you from the initial to one of the continuum states that are linearly superimposed to make your wave packet, in terms of the spectral component at resonance of the XUV electric field, and in terms of the photoelectron dispersion, which is embedded in the omega of k and which is trivial if you have gases, because photoelectrons then go through vacuum, you know, omega k is k squared over 2, and which is not trivial if you release photoelectrons inside a cluster, inside a solid. So these three are determinants, so to speak, of the photoelectron wave packet, of how it looks like. So here it is again. And so you can then, with regard to the photoelectron wave packet, say, well, I basically have a plane wave expansion of this running photoelectron wave packet with coefficients A. And these coefficients are complex, and I write them as a magnitude that is not so interesting for us today, and a phase. And this phase is very interesting. E is real, the dipole matrix element is complex, so the phase of this expansion coefficient is equal to the phase of the dipole matrix element, which will play a crucial role here. Okay? And then if you look at a sketch of these expansion coefficients of the photoelectron wave packet, the dipole matrix element will fall off at typical k values. The field, the spectral profile of the field will be peaked somewhere, assume it's Gaussian. So overall this A will be peaked somewhere detuned slightly to the red of the incident XUV pulse. And that's called that place where it's tuned, that momentum of wave number k max. Okay, that then points you towards looking at the photoelectron wave packet again, knowing that this amplitude function peaks, and to expand the phase of the dipole matrix element that you find in the exponential about this peak position that's done here. Then you get several terms. Some terms don't matter. This first zeroth order term doesn't matter because it's an overall phase that you cannot observe. This term with k max here doesn't matter. Again, it's a constant overall phase. So the first term that matters goes with k, the photoelectron momentum, and the derivative of the dipole matrix element, which has the dimension of a length and which you can interpret as a phase shift, which is here. So if you then write this photoelectron wave packet probability density in a more suggestive way, you put in this shift, so this is again the derivative of the dipole matrix element, and it reads as if you had the same wave packet that you started out with, but each component, each spectral component is shifted, right? So you have a shift. Now, shifted relative to what?
Excuse me, you make an expansion of the exponential
Taylor
expansion?
Yeah, you just...
You neglected all the other terms?
You neglect all the other terms.
And you're sure that e to the something small can be neglected?
You assume this. You assume this. To set the stage, right? Of course, we can, for simple targets, we can do ab initio calculations, and I'll show you that to verify whether this works or not. So we'll get to that. So you have this delay, the shift relative to a hypothetical reference wave packet. That would be a wave packet that looks like the photoelectron wave packet that you actually generate, but is not shifted. Of course, that cannot be measured in the experiment. Right? And those wave packets travel with a group velocity, d omega by dk. So if you know a displacement and a velocity, you can get a time or a temporal shift. I call it tx. And that's called the group velocity delay. That again depends on the derivative of the phase of the dipole matrix element and the photoelectron dispersion. This I already mentioned, and again it's determined, this group velocity delay is determined by the dipole coupling, by the spectrum of the XUV pulse, and by photoelectron dispersion. And here it is again, as it was put forward in the 40s and 50s and discussed by Eisenbud, Wigner, and Smith. And you find a nice review in this paper by Carvalho and Nussenzweig on various ways of defining delays, mostly in a particle scattering context. So we are translating what has been done for particle scattering in a way to photo emission, half scattering, as you can look at it too. So here's an interpretation. If you view this reference wave packet here as a photoelectron that moves uniformly, then the actual photoelectron wave packet you get at large times, neglect long-range interactions, and then simply interpolate this uniform motion backwards. So to get an intersect with the time axis at tx, at the group velocity delay, and to get an intersect with the position axis at the wavefront shift I mentioned earlier. Okay. Now, let's go to how to actually measure these delays. And that's done by streaking. For those of you not familiar with that, that means that you take an XUV pulse, release a photoelectron, and then expose that photoelectron additionally to an infrared pulse at a certain delay. So the peak of the infrared pulse can be delayed relative to Ex. This tau can be tuned. And what you then have is at time tau a released photoelectron that has to make its way to the detector and is influenced by the infrared electric field. Classically, you can calculate this. You solve Newton's equations. And you get the momentum of the photoelectron at the detector as the momentum at the time of release by the XUV, instantaneous pulse, so to speak, minus the infrared vector potential. At that time, the electron is born in the electric field, right? So that's a very simple expression. So you expect the photoelectron to have a momentum as it hits the detector. That momentum gets shifted up and down, or its energy gets shifted up and down, and that shift is just 180 degrees out of phase with the vector potential. That's streaking in its simplest form. If you look at this a little more careful, of course you ask, well, does the infrared field do anything else? Is that a good approximation? Remember, this is just a hand-waving, mostly classical picture of streaking. How does the infrared field influence the initial state? It may polarize it. That will show up in the electron distribution. How does it influence the final state? Is the electron really free on its way to detector? No. Is it just influenced by the infrared laser field? No. Does it feel other forces? Yes. Which other forces? Forces due to the Coulomb interaction with the residual ion. So those points we need to address next. And that's done here. Again, a little schematically, but you get the idea. So the perturbation or polarization of the initial state by the infrared field leads, in a simple two-level picture, to a mixture of one or several excited states. I take one with an excited state amplitude h that you can, again, in the simplest case, derive in first order, and you get this expression for the excited state amplitude in terms of the excitation dipole matrix element and in terms of the detuning between the excitation energy and the actual infrared photon energy. Right? That's a known expression, and this excited state fraction, of course, oscillates with time. You have all seen it. And so effectively what you then have is you don't just have the dipole matrix element I showed you before being the essence of the coupling to the continuum, but you have a dipole matrix element that is modified by this excited state fraction. So if you take this calculated excited state fraction and put it here, basically you get an effective, if you wish, matrix element that depends on tau and that contains typically ratios between excitation and ionization matrix elements. So I'll copy this over. Here it is again. And let me call this corrective factor D. So that's, if D is different from 1, you have a perturbed initial state. And so if the dipole matrix element is perturbed, you can already see how things go. The phase of the dipole matrix element is changed. Therefore, the group velocity delay is changed. And that's shown here. And typically, what you get is the group velocity delay that you would have without this initial state polarization, plus an extra term, which is characterized by this coherent superposition of two paths to the continuum from the initial and from the excited state. Right? So you can use this as Stark mixing, and you emit out of the Stark mixed states. And note there's an oscillatory time dependence also, or delay dependence embedded in this factor D that will come handy. So here are some numerical results. Just an example. This is hydrogen ab initio put on a numerical grid. We start in the 2s state. We switch on the fields. We propagate to the XUV field that mostly ionizes, and then streak in the infrared field, which mostly Stark mixes the 2s with the 2p0 state. We have linearly polarized light. And then here you see so-called streaking traces. Unpolarized means that we do not include this target perturbation, and polarized means we do include it. And you see strong differences in photoelectron dispersion. And if you take the spectral average over each of these streaking traces separately, then you get these what we call centers of energies. And so even though the spectrograms are very different due to polarization, as a lucky circumstance here, by spectrally averaging, you lose all this information. And so you have no phase shift between these curves for the polarized and for the undistorted target, and you would predict no streaking time delay as a result. Now let's move to the final state. The final state, in the most elementary quantum mechanical way of describing it, is described in terms of a Volkov wave, simply because a Volkov wave is an analytical expression, an analytical solution of Schrödinger's equation for an electron in a CW laser field. That's very convenient. That's why everybody uses it. Is it good enough? Well, let's see. So let me just remind you what a Volkov wave is. It has an amplitude that is irrelevant for this discussion. It has the typical stationary state, time dependence, and it has an extra phase term or an extra action. And that action is simply given in terms of the photoelectron momentum and the electric field or the vector potential A of the streaking field. So that's a very simple, convenient expression. As in classical mechanics, if you take the time derivative of an action, you get an energy shift. And so K, photoelectron momentum, times vector potential, as in the classical model I just showed you, gives you the streaking shift, this periodic up and down that you have just seen. And again, it's 100 degrees, 180 degrees out of phase with the driving vector potential. Right? So it's a convenient reference for theorists. Experimentalists can only measure relative time delays, and we get to that. Now here are some numerical examples for our test system because it's computationally convenient, one-dimensional hydrogen with a soft core parameter fitted to at least produce the right ionization energy, 13.6 eV. And that's a full exact calculation within this model of the streaking trace. This is the SFA calculation. If you look at the two, you see a little bit of a difference. So you have a different spectral profile here as opposed to here of the photoelectron wave packet, meaning you have also different temporal profile. If you take the spectral averages here, then you see what you don't see from the spectra, namely that the lines are shifted. Shifted by 55 attoseconds. That is small, but that can be resolved in experiments. That can resolve shifts of the order of 10 attoseconds. So this matters. So deviations from the pure Volkov description of the final state for the electron do matter in a testable way. It's interesting to plot this time delay, so 55 attoseconds for example, as a function of the XUV energy. And you see that relative to the SFA prediction, strong field approximation, Volkov prediction, this delay goes to 0. As it has to, because as the photoelectron gets out faster and faster, as the XUV photons get bigger and bigger, there is no time for complicated interactions. Right? And simultaneously, the amplitude enhancement capital K that you have in the streaking amplitude also goes to 1. And you fall back, so to speak, in the high energy limit to what is very well understood, namely the strong field approximation streaking result. Okay, so now let's go beyond this SFA result, because we have seen it matters. It makes of the order of 50 attosecond shifts or more, depending on your parameters. And one way to do better is to perform a semiclassical calculation where you say my final state has an amplitude, which doesn't matter for this discussion, and a phase term. The phase term has the k squared over 2 energy of a free electron for this atomic example, and has a correction as a phase, written as a phase is an action. So this correction in a semi-classical approach is calculated classically. So you have a quantum wave function, but you classically calculate this phase. That makes the semi-classical combination. And you do this by either saying, well, I turn the infrared field off, then I calculate this action along straight line path of a photoelectron, or I turn it on, and then I have the influence of the infrared field, and so these electrons start to wiggle. This is schematic. You sample over all the path, of course, right? And then you get this Eikenhorn approximation expression for the phase in terms of a zeroth order term, which is again the strong field, and a corrective term. And this corrective term includes everything that the strong field approximation or the Volkov state does not. For example, the interaction, the simultaneous interaction of the photoelectron with the laser as it is driven around, and the residual ion, as you will see. So let's parameterize this. So here the deviation between the free and the laser-driven trajectory is easily computed. That's here. Let's see, that should come in. Okay. And depends, again, on the laser field. The laser fields are sufficiently weak, 10 to the 11 watts per square centimeter, so that delta X can be considered small. Then it's clear what you do. You expand the Eikenhorn phase in delta X and keep in this correction the first linear term in A or in delta X. And that's what you get. And that's an interesting expression. Why? Because it tells you the Volkov approximation would only include in the final state the photoelectron's interaction with the laser. Here we now have a corrective term where you simultaneously have the interaction with the laser through A, but also the Coulombic force as this emitted electron leaves a positive charge behind. And that's included in this ionic potential here. Right? So then the rest is straightforward. This is an action. A time derivative of an action gives you an energy shift. You X this out, and you find in this now corrected energy shift the strong field approximation result, minus k times A, that you've seen before, and two terms in addition, of which this term that convolutes the Coulomb with the laser interaction matters most. And so you can adjust that by the form of the infrared pulse and calculate an enhancement, amplitude enhancement, and a relative temporal shift, so relative to SFA, including these extra effects that you don't have. Here are examples. The top graph really only matters where we compare these Eikenhorn results with SFA, and you see there's a shift, so it does matter. And then if you look at how this shift, this temporal shift relative to the Volkov calculation, to the SFA, behaves as you go to bigger and bigger XUV photons, again you see that it tends to vanish. So again, in a high energy limit, you find the strong field approximation as a test, as a limiting case. And you do this, you find this for the time delay, the group velocity time delay, and also for the enhancement, the amplitude enhancement. So that's all good so far, but can't be measured. In order to measure time delays, you have to have a reference. And the simplest way, of course, to do this is to say, well, instead of photo emitting from just one state, I photo emit from two, then I get two streaking traces. They're typically energetically separated, so you can easily distinguish them in different spectral regions. And then I do the spectral average. That gets me to the centers of energy. And those may or may not show a phase shift. If they show a phase shift, that corresponds to a time delay. And that's what everybody is doing. And here's the perhaps most famous example. That's an experiment that was done a couple of years ago. The debate on what it exactly means is going on. It's not over, will not be over, I have the impression, for another 5 years. Because this is photo emission from the 2s and the 2p levels of neon compared. And this photo emission is time delayed. You don't see this in the spectra, in the streaking traces, but if you do the centers of energies, then you get to a time delay of 21 attoseconds. And all quantum calculations that have been tried on this system by various groups fail to reproduce this factor of 21 attoseconds by a lot, by at least a factor of 2. This would be a talk by itself, I just want to point out there's a calculation by the Belfast group that is fully correlated, that includes the electron correlation in neon at a rather high level, and still it doesn't get to the measured result. Kind of ironically, we put together a simple classical model starting with a microcanonical ensemble for the initial states, and we get 15 attoseconds with electronic and 6 without electronic correlation. There's a little serendipity involved in this, so I don't want to over-advertise. But it indicates electronic correlation plays into this time delay a lot. Now, to the second part of my talk, surfaces. 5 minutes, okay, so I'll go a few minutes in the discussion. So here is an example where you generate an XUV pulse from the same infrared pulse that is then, you make higher harmonics, you cut out the plateau region in the higher harmonics, you have a delayable mirror set up, and then you bombard a surface with an XUV pulse and a delayed streaking infrared pulse, and again you get streaking traces. So that was done in 2007 in the first proof of principles experiment here for solid targets, and it was found that the emission from the 4F core and the conduction band is delayed by 110 attoseconds. Right? And that was found again by not looking directly at the spectra but at the centers of energy. As before, 110 attoseconds was the delay between localized core levels, I have it again here, so localized 4F core levels and conduction band levels. We calculated this, and the basic model I want to run you through briefly here, assuming that we have an initial state band, either a very narrow 4F fine structure split level band or a conduction band that we build with Bloch waves, incident plus reflected, matched to an exponential tail, so to have standing waves in the surface, from which electrons get emitted into modified Volkov states, so that we can calculate the transition amplitude, so from the initial state in a band to a modified Volkov state, and these electrons are kicked out by the XUV electric field. Once we have that, we can just incoherently sum all these contributions over the first Bryoma zone to get an observable, the photoemission probability as a function of, say, the delay that can be measured. Okay, the initial state is a Bloch wave. I won't say much about this. The final state, perhaps, is a little more interesting, is a Volkov state in the simplest version of this model, where we have here the Volkov phase, and where we have here a complex momentum that we use in order to describe damping. So photoelectron propagation through the solid in the simplest version of our model is described just by a mean free path lambda that includes all the elastic and inelastic scattering processes, when that's the Volkov phase. So we do this calculation, we compute, as we did for atoms, streaking traces for the conduction band and for the 4F core level emission. We build these centers of energies carefully in exactly the same way as the experimentalists do it over exactly the same spectral ranges. Everything is very sensitive. If you don't do this, you can compare. And if we adjust the only free parameter, the mean free path, to 5 atomic units, we reproduce the experiment. Okay, that's fine. Does this work for other targets, or is this just a serendipitous, lucky coincidence? We tried this also for magnesium. So there were a more recent experiment was done on thin films of magnesium, 0001, 30 layers thick, in Garching. And here we beefed up our model a little bit by using Sokhov-Chulkov potentials for the initial state. Those are effective one-electron potentials that are fitted to density functional calculations in different ways for the valence band and for the conduction band. We obtained one of the mean free paths, namely those for the valence electrons, by fit to synchrotron radiation spectra that are around for a long time, and left the other mean free path as the only open parameter to be determined. And we determined it to 5 angstroms, and then could compare the calculated streaking traces for the valence band and 2p emission with the experiment. For a chirped XUV pulse with a chirp of 2, here's a comparison for a different chirp, and you see for the 2p emission, the chirp of the pulse really matters. The rest is business as usual. You build the streaking traces. You then calculate the centers of energies, and you find, in agreement with the experiment, that there is no delay. Okay, so there's some truth to this model, we think. Then, of course, you can go on. There's a lot of parameters to play. You can look at what happens for 30 monolayers, experiment and calculations. That's what I just shown you. These results yield 0 relative time delay. Or you can increase the film thickness. If you increase the film thickness, theorists can do that easily, you change the streaking amplitude, you change the photoelectron dispersion. You therefore change also, here in green, the relative delay between the core level and the valence band emission over a range of about 100 attoseconds. So these results are sensitive to the film thickness. If everything else were known, so to speak, in this experiment, you could measure, by measuring the streaking delay, you could measure the thickness of a thin film if everything else were settled. There are many more scenarios that I could discuss. I don't have time. You can put adsorbents on the surface and then ask what is the delay between an Auger and a core level electron. You can study the core hole dynamics. What is the delay between the Auger and the solid state electrons? No time. But I want to also, with regard to the previous talk, focus briefly on plasmonic excitations. Now, waiting for critical looks. You're still smiling and friendly. So, oh, that's plenty of time. So the basic idea is that if you emit a photoelectron, that photoelectron in a complex target, say in a metal surface, generates an image charge. And everybody here is familiar with the image charge concept. It is really a redistribution of surface charge dynamically that, seen from the outside by the photoelectron, can be described by a fictitious charge at the same distance from the interface with the opposite sign. That's the image charge concept. Holds for perfect metals. Now, at the attosecond time scale, this picture is no longer good, right? Because these image charges are built up by surface charges, which can be, yesterday somebody said it depends on the basis, use a plasmonic basis, so they can be viewed as plasmons that redistribute on the plasmon time scale, right? So this redistribution will happen at a, say, 50 attosecond time scale. Therefore, you may already guess, it matters if you have attosecond precision in the experiment. And so what we then need is not this simple image charge concept, but we need the full plasmon dynamics and ask the question, can it be probed? Can it be probed with streaking experiments? So the first step then is to describe that. And this is just a second quantization Hamiltonian. Looks scary, but it just does the bookkeeping right. That's really all it does. Where we insert heuristic dispersion relations for bulk and surface plasmons, so to describe the motion of these charges, basically. We then say, just for the sake of calculating an effective time-dependent generalized image potential, we look at this electron classically. So here's the density of a classically moving photoelectron, and then calculate the interaction Hamiltonian. So calculate how this electron excites surface and bulk plasmons. That looks ugly. You don't need to look too careful. This is all basically known for a long time. We just applied it to our scenario. It then turns out that you can calculate the dynamical image potential without further approximations. You go through 2 or 3 pages of paper, and you get an effective potential with a real and imaginary part. The real part, don't look at it too closely, has the right asymptotic behavior at large distances. It has to go to the image potential. The imaginary part at slow velocities has to be 0 because you won't excite any real nor virtual plasmons. And then this is the simple picture, right? So this is a high-speed photograph of a pebble thrown in a lake. The pebble is the XUV photon, and little water droplets spill out. And so the picture we have here is this water droplet has generated a plasmon, which then acts back on it. That makes this back interaction, makes the factor 1/2 to avoid double counting. Right, and then, of course, you want to see numerically, how does it work? Is it of relevance or not? So we used a thin aluminum film and did 2 calculations with a static potential, generated eigenfunctions, and then used those occupied states as a source term released by the XUV and propagated in the laser field. And then we did the same with the dynamical image potential propagated through the laser field. And then you can compare streaking traces for the dynamical, for the static calculation, do the spectral averaging, get to the centers of energy, and then you actually see there's a difference. So these centers of energies are shifted by 100 attoseconds. So the dynamical build-up and decay of image charges at an attosecond timescale matters and should clearly be observable. Right? And then the rest, we did many more studies. You see, for instance, the delay depends on the XUV energy. You see remnants of plasmon excitation, peaks that are spaced by about the plasmon energy. All of this depends on the mean free path. If you have a larger mean free path, you have a larger amplitude because the photoelectron interacts longer inside the solid. This depends on the electron density. If you have a different electron density, you change the plasmon frequency, you change the plasmon energy, and so on and so forth. And so I want to just end with concluding that there's a lot to do. The question of what reference state we use is still open. I think taking, for example, a surface state or an image state as a reference would be great, because those electrons wouldn't have to propagate through the solid, and then use this reference to compare with emission from an inner state inside the target, where you are sensitive to propagation effects, for example. A lot is actually not known. The infrared skin depth at high intensities is a matter of debate. It is much shorter than you would expect by reading Jackson's classical electrodynamic. The influence of surface charges, plasmonic near field effects is not known. And so there's a whole field of studies that you could imagine take off from there. And with this, I want to thank you all. It matters. It matters at the scale of the experimental resolution, which is of the order 10 attoseconds. Right. But you could imagine an yeah, but you could imagine a concrete experiment here. For instance, say you have a surface and you take emission from a surface state as a reference, right? And compare that to emission from conduction band or core level states. So you have two streaking traces. The surface state emission as a reference, and then the electrons from the, say, core level states that first have to make their way out of the bulk, and along the way will excite much more likely plasmons. Then you have the two streaking traces, you compare them, and you get a relative streaking delay. The message here is this relative streaking delay will depend on whether you allow for dynamical plasmon response or whether you don't. This is an approximation. There are model assumptions, of course, so give or take 30 attoseconds. Still, even if you boil this down to, say, 40 attoseconds, it would still be a very short time, but it would be a significant time at the scale of relative streaking delays as that can be measured.
So am I right or not? I mean, just to clarify. So if you include the Coulomb interaction for the final state, so then this is kind of reason physically for this shift in time delay, right?
Yeah, that's a shift associated with that, exactly, yeah.
So in principle, as far as understood, as far as I remember, Volkov doesn't include this at all, right?
That's correct. It's absolutely correct. I'm sure I'll get to this quickly enough.
And in your case, actually, your fields are weak, right? Or how strong?
That depends. Typically, the streaking fields are 10 to the 11 to 10 to 12 watts per square centimeter.
Can you still apply the perturbation theory or not?
No, that's why the streaking field ends up in the exponent.